Hello everyone, I'm going to show you how we can use Excel to plot out a titration curve. I've done that a few months ago for the consolidation test which I've set for the students. So for this particular question, we have aqueous ammonia being pipetted out. It is being placed in the conical flask, and the burette, we have a strong acid, in this case hydrochloric acid, and is being added dropwise, and this titration curve is being plotted out. Yeah, so today I'm going to show you how this can be done. Of course, before you do it, you need to have some predetermined concentration of aqueous ammonia and hydrochloric acid in mind, so that you can work it out quite easily. Okay, so first of all, we'll begin by having the concentration of ammonia. In our case here, I've used 0.100 moles per dm cube. Okay, yep. So I'm just going to type it in 0.100. Okay, so normally it will be a good habit for you to write out the terms and the units. Okay, so again, I'm going to do the same in moles per dm cube, and then the next thing is I'm going to write out the volume of ammonia which I have pipetted out. Okay, so the volume will be in terms of cubic centimeters, so that it's easier for our case, because that is the volume which we normally talk about when we pipette things. Okay, and then the pKb in question of ammonia, NH3. Okay, so for pKb, it really depends on you. You can go and search the information on the World Wide Web, which is usually available, 4.74, and then the concentration of hydrochloric acid as well. So in our case here, I think we use a slightly different concentration, that's 0.125 moles per dm cube. Yeah, all these are the variables which you can change according to the question. Yeah, and you can change to a different strong and weak acid. Yeah, so I'll leave it to you how you want to go about changing the variable, and thereafter the titration curve will look different. Then after that, the next part will have the amount of HCl required for complete neutralizations. Okay, I'm just going to put this in. Amounts, I'm going to use the Greek symbol. Okay, which we often use. So yeah, so this is the one, amount of okay, so there's a bit of mishap here, so I'm just going to change this to calibre. Yeah, so the amount of HCl required for complete neutralization. Okay, so that will be in terms of moles, so just cancel everything else. Yep. And how can we do that? We can do that easily by simply taking the volume in dm cube, and then multiply by the concentration of ammonia. The reason being because hydrochloric acid and ammonia react in a 1:1 ratio. Okay, and what about the volume of HCl required? Okay, so this can be done easily as well. Okay, that will simply be taking the amount divided by the concentration of HCl, and then we scale it to 1000, because again, the usual volume which we are comfortable with is in cubic centimeters. Yeah, and you should also be aware that in the course of our calculation, we might need to determine the pH at the equivalence point. So that means that the concentration of ammonium at the equivalence point is very important. Yeah, so we are going to do that over here. Okay, so I'm going to change this to superscript. This is the concentration of ammonium at the equivalence point. Okay, in moles per dm cube. How are we going to calculate that? We need to take into consideration that, or we need to be aware that the amount of ammonium is the same as the amount of ammonia I have at the start. Yeah, so that would be 2.00 times 10 to the power minus 3. Yeah, but there's dilution involved because at the beginning I have 20.0 cubic centimeters. Yeah, but now I have 16.0 extra. Yeah, because of the hydrochloric acid being added. Yeah, and from here, this will be the concentration in moles per cubic centimeters. I need to scale to 1000. Okay, so this is the concentration I'm getting, 0.0556 or 5.56 times 10 to the power minus 2. Yeah, from here I need to calculate initial pH, okay, of aqueous ammonia. Yeah, and how to calculate that, I think it shouldn't be a major issue because you know that ammonia ionizes partially in water to give us ammonium and OH minus. So if we have an ice table, we know that the concentration of ammonia at the beginning is 0.100. Okay, and we assume that A amount ionizes. Okay, so the equilibrium concentration of aqueous ammonia will then be 0.100 minus A, and the equilibrium concentration of ammonium and hydroxide will be OH, will be A each, and therefore Kb will be A squared over 0.100 minus A. We can actually perform an approximation here, which in most cases makes perfect sense, because A, we will assume A is much smaller than 0.100 moles per dm cube. Yeah, so from here we can determine A to be square root of Kb multiplied by 0.100. Okay, yeah, then we can easily input this particular formula into our cell and calculate and determine the pH. Yeah, some of you might be wondering, since we are using Excel, we don't have to do approximation. Am I right to say that? Yeah, you need not use approximation if you don't wish to, or if you wish to, but do take note that the value will be around the same, so it's actually easier to use the approximation in our calculation, so that I think the values calculated will be neater, and the cells will not be, the formula we input will not be overly complicated. Okay, so we can always take reference to this. Yeah, and then we can easily use this in our calculation. Okay, so with that, I'm going to just put it in. So that will be equals to, remember that we're calculating pH here. So from what we have earlier on, the calculation, we are getting the concentration of OH minus. Yeah, so and if we take a minus log base 10 of that concentration of OH minus, we are getting POH. So I think the first thing we need to do is to take 14 minus of the log base 10 of what we wish to calculate. Okay, so log base 10, so that's log base 10. Log base 10 of what? So log base 10 of our let's see what we have over here. So concentration first. Okay, multiply by 10 to the power of minus 4.74. Okay, so we have this, and then to the power of 0.5. Okay, so we get 11.13. I think there's a little bit of incorrect thing I've input in the formula, but the Excel corrected it for me, so I should get 11.13. Yeah, so the next thing you want to ask yourself is, does this make perfect sense? Of course, because it's a weak base, so we are not going to expect the pH to be close to 13 or 14. Yeah, so I think 11.13, about 100 times smaller, I think that's fine. Okay, then what about the pH at equivalence points, or rather at half equivalence points? Yeah, this can be done quite easily. So that simply equals to 14 minus the pKb. So that should be 9.26. Okay, what about the Ka of ammonium, NH4 plus? Yeah, can that be done? Can that be done easily as well? Yeah, that can be determined quite easily, because we know the formula with respect to the pKw. Okay, so let's try to do it. So our ammonium, okay, so we can do that by simply just taking pKw, so that's 10 to the power, or rather kW, that's 10 to the power of minus 14, divide by 10 to the power of minus 4.74. Okay, we can do that. So that will be 5.495 times 10 to the power minus 10. Okay, so what about the pH at the equivalence points? Okay, can we determine the pH at the equivalence point? Yep. So that can be done quite easily. Yeah, because we know that let me just change the color of the ink. We know that ammonium will ionize partially in water to give us ammonia and H plus. So if we have an I stable, we have 0.0556 and then dash dash and then minus B plus B plus B, and then this equilibrium concentration of ammonium, that's 0.0556 minus B, BB. From here, Ka, which is what we have found earlier on, is equals to B squared over 0.0556 minus B. Yeah, so again we can make an approximation. So assume B is much smaller than 0.0556. Yep, and then B is therefore square root of Ka multiplied by 0.0556. Okay, and the B here we obtain is essentially the H plus concentration, and therefore pH is simply minus log base 10 of this whole expression of B. Okay, yep, so we can definitely do that quite easily. Okay, so we're just going to translate that into the cell. So that will be equals to minus log base 10. Okay, log base 10. I'm going to input the numbers. Okay, so that will be concentration of this ammonium, okay, multiplied by the Ka, okay, and then to the power of 0.5. Okay, so that will, so we get 5.26 over here. So that's the pH at the equivalence point. Okay, yep. So once we are done with all this calculation, we are ready to plot our titration curve. Okay, yep. So I'm just going to populate some columns. So the first thing I'm going to do is have the volume of HCl added. Okay, and also next will be the volume of HCl added in dm cube. Okay, because it's actually easier to calculate in dm cube. And then the next thing we're going to do is we're going to determine the amount of ammonium formed. Okay, so I'm just going to put here amount of ammonium. So I'm going to put the Greek symbol. Okay, amount of ammonium formed. Okay, so that's superscript amount of ammonium formed. Okay, and then next is the amount of ammonia remaining. Okay, which can be done quite easily as well. Okay, and then the pH. The next column is the pH. Okay. I think first we will just have we will just start from 0, because at the beginning we have 0 cubic centimeters of HCl being added, and then we can go in steps by 0.5, or if not in between we can have a 0.25 if we wish to. Yeah, and then I will drag all the way to the equivalence point. That will be 16, but I will want to drag beyond that because I want to complete the titration curve. So maybe I'll drag all the way to the 30. Okay, and then I will determine the volume of HCl in dm cube. So that will be equals to this divided by 1000, and then I'll just drag it all the way down to 30. Okay, I will need 2 key points. Okay, so over here I'll just highlight this, maybe in orange. Okay, so this I can simply just input the pH. So the pH of the equivalence point will therefore be 5.26. Okay, and then the initial pH, I can also just input it. The initial pH is 11.13. Okay, so yeah, so this is also something which I can just color code, maybe in light green. Okay, okay, then after that I'm going to continue populating the cell, okay, by determining the amount of ammonium formed. So the amount of the amount of ammonium formed is simply the amount of hydrochloric acid added. Yeah, so that will be equals to the volume of hydrochloric acid added multiplied by its concentration. So that's 0.125. So I'm going to get this particular number. But I can't simply just drag down like this, because the whole thing will be messed up, because the cell F4, in this case the concentration of HCl, is fixed. So I'm going to put in the $sign to tell us that it's fixed, and then I'm just going to drag it all the way down. Okay, but I'm not going to drag it all the way down to beyond the equivalence points, okay, until slightly before the equivalence point. That's 15.75. Yeah, that will make perfect sense. Okay, then the next thing I'm going to do is to determine the amount of ammonia remaining. Okay, so that will be the amount of ammonia I've added. Okay, so essentially this 20.00 divides, divide by 1000. Okay, because we need to convert it to moles per dm cube. To convert it to dm cube, and then multiply by the concentration. Okay, so this will be the amount of ammonia I have at the start. Yeah, but remember this, for the cell we need to ensure that they are fixed, because these are fixed variables. So it's important to put them in first to be the fixed variable. Okay, and then we need to format the cell to make sure that it reflects the correct number of decimal place, and then we will then subtract this off from the ammonium being formed, which is over here. So we get 0.00194. Okay, and then I will just drag all the way down. Just make sure that the numbers are correct. If you wish to verify, you can just punch in your calculator. Okay, but just be careful not to drag beyond the equivalence points. Okay, and then we get something like this. Okay, because all these things are what we require in order to calculate the pH. Okay, yeah. Then the next thing I'm going to do, right, is to determine the pH. Essentially it will be similar, because I need the ratio of I will need, okay, so basically for the KBX, so for KB here, KB essentially is the concentration of ammonium multiplied by concentration of OH minus divided by the concentration of ammonia. Okay, so therefore, right, the concentration of OH minus essentially is a ratio between ammonia and ammonium. So that's KB multiplied by ammonia divided by ammonium. Okay, so we need to have this formula in mind. And then this is this is concentration of OH minus. So we need to input this into our cell. And do we know the ratio? Yes, we do know the ratio. The ratio essentially is the cell is this cell over this cell. Okay, ammonia over ammonium. Yeah, so okay, I'm just going to determine the pH by inputting this formula into the cell. Okay, so essentially I think first we will just equate the KB. Okay, so that will be 10 to the power of 4.74. so that's the KB here. But we know that this cell is fixed, so we're going to put a $sign. Okay, and multiply by this particular cell divide by this particular cell. Okay, and then we just put an equal sign over here. Okay, so 10 to the power there's a minus sign which I forgot to input. Okay, and then after that we're going to take minus log base 10 of this whole thing. Okay, so I'm just going to put this. Okay, and then this is POH, and then we are just going to take 14 minus this whole thing. Okay, and I'm going to get 10.75. So we keep it to 2 decimal place. Okay, so that's 10.75. Okay, so with the same formula, I'm just going to drag it all the way down. Okay, in a similar way until slightly before the equivalence point. So I'm going to get 7.46. Okay, so I think from here you can see that we are about to be able to plot some things. Okay, but this is just the titration curve until the equivalence points. Okay, what about like after that? Yeah, so what should we do after that? How are we going to calculate the pH? Okay, now we know that after that, right, the pH is largely due to the amount or the extra amount of hydrochloric acid we have added into the system. We do this by taking the difference between the volume at 16.25 cubic centimeters and the equivalence volume. Okay, the equivalence volume will be fixed. Okay, so we're going to put a dollar sign here to indicate that it's a fixed volume we are going to multiply. Or rather we're going to subtract from, and then we multiply it by the concentration term. So the concentration term is here 0.125 moles per dm cube. Okay, so again the concentration term is a fixed term, so we're going to put a dollar sign. Okay, and then we're going to use this, right, to let's put in one more bracket to make it clearer. Okay, and we will divide this by the total volume. Okay, so the total volume will be the summation of the initial pipetted volume, which is 20.0. But do take note that this is in cubic centimeters. Okay, so again, let us remind ourselves to put a dollar sign. We need to multiply by 0.001. Okay, in order for it to be scaled to dm cube, and then we need to add the volume term, in this case 0.01625. okay, yeah, so this is going to give us the concentration of H plus at that volume. Okay, the excess, or rather, okay, let's try again. The concentration of the excess H plus, okay, at that volume. Okay, but if you are supposed to find pH, then we have to take the negative log base 10 of this particular term. Okay, so we're going to put another bracket here, because we are going to take the minus log base 10 of this. Okay, so minus log. Okay, so we're just going to put equates, and then we're going to get 3.06. Okay, yep. So before you do anything, please check your formula, make sure everything is correct. Okay, so that's the difference between the two volume, the volume at 16.25 and the volume of the equivalence point. You have to fix this, multiply by the concentration of hydrochloric acid, you have to fix it as well, divide by a fixed volume pipetted out, which is 20.0, you scale it to dm cube, and then you add to the extra volume, or rather the volume of HCl introduced into the system, and then you take minus log base 10 of the whole term, because that will be the concentration of H plus at 16.25 cubic centimeters. Okay, after we are done, we'll drag this down all the way to 30. Okay, and then we'll get about 1.46. Okay, right, so you see, now we have all the pH values and all the volume terms. Okay, so I think we are ready to plot a graph. Okay, so let us plot a graph. Yep, so I'm going to just highlight all the terms here. Okay, and then highlight all the terms here. Okay, we're just going to introduce the scattered plots, which is being introduced in my first video. Okay, so I'm going to plot scatter plots. Okay, you notice that this is very similar to a titration curve, okay, which we are quite familiar with. Okay, so I'm just going to click the title. Okay, okay, I'm just going to introduce this into a new cell, so I'm going to move the chart into a new sheet. Okay, yeah, just going to shift the chart around. All right, okay, I'm going to zoom in a little bit because it's not so clear. Okay, so you notice that you have all the points here, and then you get a very nice titration curve, right? Yep, and then we're gonna have all the volume terms. Okay, you notice that in the question which I said, right, they are all being changed to one without decimal place. The reason being very simple, because with the decimal place, I think it will make the printing a little ugly. So it's really up to you. Yeah. So if you wish to, we can change the format the major axis, which we have always been doing. Okay. So again, this is how we can beautify the graph. Okay. So just going to input the necessary lines, which I think I've mentioned to you in the previous videos. Okay, so this is the formatting on the major axis. Okay, and then yep, everything seems okay. And then going to change the axis label, so it's from 0 to 35. So again, if you recall, if you want to put in the arrows, yeah, so I think we can't reach 35, so maybe we have until 32. Shall we do that? Okay, so make sure to remember to change to 0, and the major axis, probably you want it to be in steps of 2 cubic centimeters. Would that be okay? Okay, and then the minor one, I think 0.2 is okay, but it doesn't really matter here. The tick sign, the tick marks will be, sorry, the major will be across. I think that will look decently nice. Okay, and then we'll end with an arrow. So let's try whether we, yeah, so the arrow type is like that. Okay, so yeah, in this case we also have the label at 32, right? So you see that there's this label over here with 32, so it looks a bit ugly. So I think we have to change the axis as well over here. Then I think we have to change it to say 31.5. Okay, so that it wouldn't get the labels, so something like this. I think that will look nice. Okay, then we try it for the major axis. Okay, so for the major axis, we go from I think we go until 11.5. That's fine. Okay, then of course we start from 0. The major one, maybe we have 1 and then 0.1. I think this makes a little bit more sense. The tick marks will be outside. Okay, and I think that's fine, and then we're just going to have it dark. Okay, and then maybe the arrow, end arrow. Okay, so the end arrow will look like this, something like this. So I think everything else is great. Fade, we're going to format major axis. Okay, so we have this line in, so everything else looks decent. Okay, yeah, if you think that the lines are a little bit distracting for the major axis, you can actually make it a little transparent, let's say 20%. Okay, and then we'll do the same to the horizontal ones, which is 20%. Okay, then it will look a little lighter. Yeah, and then when you input your trend line, so you can't really add trend line. I think we should format data series, and then we have a solid line, something like that. Can you see the solid line? We shouldn't be adding trend line, because for trend line, they will try to either plot it to fit into a linear fashion or a logarithmic fashion or any power series. So we will try to fit all the lines into a nice trend line. And then in our case here, you notice that in the question I said it doesn't have a marker. Oh, sorry, it doesn't have the plotted points. That is deliberate, because I think it will look very ugly with the plotted points. Yeah, so for the marker here, I'm just going to put no marker option. Okay, so I think everything else will look beautiful. And then of course the line, you can decide on what kind of lines you like. Okay, so I can draw it in a very nice blue. Okay, so I'm just going to choose this dark blue option. Okay, so that will be the line, and then you can choose the thickness as well. Okay, if you think it's too thick, yeah, you can adjust it. Okay, something like this. Okay, then some of you will remember that when we format the chart series, the border will have no lines. Okay, yeah, so that when we paste this whole thing over to Microsoft Word, it will look nice. Yeah, so just remember some of the tips. If you want to see the arrow head without the numbering, then you have to do a little bit of adjustment. Of course, if you wish to, you can add in the minor axis, so that you can directly read off, let's say at a half equivalence point, you can read off this point to be about 9.26. Yeah, but I think right now you can't read it off as 9.26 because the minor grid lines isn't shown. Yeah, okay, so I think I have shown you how to plot a titration curve using Excel, and of course there is a combination of different equations which are required to be used. Yeah, so basically from when we start to perform our titration, this will be from about when you add in a little bit of HCl and then all the way to before the equivalence point, we'll be largely using the KB expression. Okay, and then any excess acids added here will be largely using the amount of H plus in excess and try to calculate its concentration and its pH. Yeah, so do remember that all these are approximation. Nonetheless, they are useful in helping us to sketch out a decently looking titration curve. Okay, yep. So with that, we have come to the end of this video showcasing how to plot a titration curve using Excel. So do look out for future videos on the use of Excel in chemistry.